Okay, today's section is on solving equations and inequalities. We've kind of done this sort of thing before. Well, we're going to look at it in a slightly different way. Typically, when we solve the equations, we're trying to isolate x, get x to be all by itself, except in some of these equations, that's not very easy to do. So we're going to look at a couple of different techniques to help us out there. So here's an example. Solve cos of pi over 2 times x equal to x. What this means graphically is we want to find out where these two things are the same. So the right-hand side is a linear function, just x, y equals x. It's the blue line here on the screen. And the left-hand side is a curve. It's a cos function. What does that pi over 2 do? Stretch? I think it'll be a compression because pi over 2 is going to be bigger than 1, ever so slightly. Pi is 3.14. You divide that by 2. Oh, sorry. 3.14 divided by 2. So you'll have like a 2 point or whatever that value is, x. So we'll have to, because it's bigger than 1, we'll get a little bit of a compression. Yeah, I hear. So, so the graph is here in red. Essentially what we're asked to do is to find out this point where these two things are equal. They're equal where they cross. So we can do this a couple of different ways. I want to show you well, we haven't come up with an answer yet, right? But I mean, that's where we're headed. I want to show you a couple of things that we can do here. And you'll see this kind of come up in some of the examples that we do. The first thing that we can do is it's kind of hard, not hard, but it can be difficult to work with the equation like this. So it may be useful to collect all of the terms on one side of the equation. So that's what I'm going to do here. Which is kind of what you would normally do if you were solving an equation, certainly a quadratic equation. I'm going to subtract x from both sides, and we'll get something that's like this. So really, we want to find out where, when we take the value of our cos function and we subtract the value of our linear function, where are we going to get an answer of 0? Obviously, it's not here. If we take this value and subtract this value, we'll get a value that's more negative. So this fits in nicely with the work that we did on subtracting functions. Here we are subtracting the x, y equals x from y equals cos of pi over 2 minus x. So you can visualize that graphically the same way that you visualized the work that we did at the beginning of the week. So this is called a guess and improvement strategy in the textbook. You might call it a guess and check. I think the group that was doing this called it guess and check. Well, obviously, in order for this difference to equal 0, that's going to happen when both of the values are the same. So what we can do here is we can actually estimate on our graph a value where we're going to get these two things being the same. And so I guess 1 would be over here. And 0.5 would be over here, or 1/2. So I'm going to guess at 0.5. So that's our guess. Is x equals 1/2. So let's substitute 1/2 in for x and just see how close that guess is. Pi over 2 times 1/2 is just pi over 4. Pi over 4 is the same as 1 over root 2. We subtract 1/2 from that. It's probably a good idea to go to some approximate values. I think if you plug that into your calculator, you should get approximately 0.207. So that was our first guess. Yes, yeah. Definitely in radians. So we don't have to put a... Right. So our goal here was to get an answer equal to 0. We're kind of close, but the idea here is we want to get as close as possible. So somewhere around 0.5, we could instead now look at, well, what happens if we go to 0.4? and see if that's closer, and then we can kind of narrow things down a little bit more. Does that sort of make sense? So let's try another guess. I'll try to squeeze that right in here. So we'll substitute a 0.4 in for x. And if we do that, I get an answer of a 0.409. So we kind of went the wrong way then, right? So instead of going to the left, let's try going to the right. See if I can squeeze that in right here. Any guesses at our guess? Because that's the function. Sorry, thank you. Yeah, that should be a 0.4. Thank you, Leslie. I copied down the wrong. I copied down this one instead of this one. Who said 0.7? Awesome. How come 0.7?
Because I looked at it and said, oh, it's bigger than 0.5 by looking at it. So I guess 0.7.
We could do 0.7, but then we'll have to do 0.6 after. So why don't we just jump to right to points? And I only say that because I already know what the answer is. But 0.7 is not a bad guess, right? Yeah, let's try at 0.6.
Well, if you go down by 0.1 and it went up by like 2,
right.
So you go up by 1, we'll jump it down.
Yeah.
To 0.
Yeah.
0.0.
Something. Yeah. Let's give it a try. We went a little bit too far, yeah. Now, really? Did you put this in brackets, Leslie? Did you put this in brackets? Pi over 2 times 0.6? I didn't just do it. I wrote it down earlier. I hope I didn't make a mistake. Okay. Okay. So we're obviously closer than we have been. We were off by 0.2 here, off by 0.4 here. Now we're off by 0.01 and a little bit. Depending on how accurate you want to be, we could actually narrow this down a little bit more. If we're going to try to be more precise, where would we go? We won't do it now, but where would we go if we're trying to be more precise? Yeah, so it has to be bigger than 0.5 and less than 0.6. So maybe a 0.58 we could check, or a 0.55. I mean, you could check at 0.55 and just see how close you're getting. If you were looking for an answer to 2 decimal places, then a 0.55 or a 0.58 or 0.59. I mean, it depends. This is really close, right? Yeah, it is, in fact, it is 0.59. Yeah. How close do I want it? If on an exam I asked you to do a guess and improvement strategy, I don't want you guessing forever. I would be okay on an exam of doing that. You know, I've seen that you know what the guess and improvement strategy is. I would be okay with going this far. Your textbook, for those of you that did this section, I took the question right out of your textbook. Your textbook actually went one step further, and they tried 0.59, and that was really, really close. I forget what the answer was, but that was really close. So the point on a test or an exam would be that you understand what it means to solve this equation, the guess and improvement strategies there. You've done it a couple of times, and this to me is probably close enough, right? So if you went this far on a test, I would give you the marks. We are doing 9.6, yeah. Is that okay? Yeah. Okay. That was one way we could solve that. There was another way, which I guess is graphing. It could be by eye, or we could use some technology, right? We could actually graph this, graph this, and there's, sure, right. So when we graph, there are actually two ways that we could graph it. We could graph the two functions. We won't do it because we saw kind of where it was. So graph the functions and find their point of intersection. Which is kind of what we did in this case to at least get us started. We eyeballed the intersection, said it was somewhere around 0.5, and we kind of narrowed things down. If we were to use, graph these functions accurately on a piece of graph paper or with some graphing technology, we would probably be able to read that value off a little bit more precisely. So that's one thing that we could do. The second thing is we could actually graph the combination of the two functions by doing sort of what we did up here. So we can actually graph this function, and instead of finding the intersection point, what are we trying to find? We're trying to find the zero. So that's the second option, is graph the combined function. And find the zeros. Both of these ways accomplish the exact same thing, but just conceptually, you should understand that we can find the intersection point, or we can combine the two functions and find the zeros. Either option obviously works. Everybody all right with that? Yeah.
So if you had like a parabola and the sinusoidal, would that not be 2? And so if you're trying to solve for it, I guess you check when you have to, would it be more answer that?
Yeah, and in fact, the graphing calculators that we have kind of are the same way. You can actually solve, you can find the roots on a graphing calculator, and the way that it works is it says, hey, there are two, it doesn't actually find both of the zeros. It says, hey, what range do you want to solve for the zeros on? So you kind of say the leftmost bound is going to be x equals whatever, 5. The rightmost would be x equals 7. I want this one in here, and it kind of narrows down the search. And then if you want the other one, you kind of repeat it again. All right, here's another example. Totally different kind of example. It's funny, you put some text up there, and you guys just, put some numbers up in your English class, and everyone's like, so the average cost of a condo in Toronto in 2001 was $144,144. I would guess it's a lot higher now. In fact, we can figure out what it is now, but. And it increased by 6.6% each year. In Regina, the average cost was $72,500, so about half. But it increased at a rate of 10% per year instead of 6.6%. This did happen. There was a big housing boom in Regina. Prices were increasing quite quickly. Sorry, condos and houses. So if these rates continue, so if both rates continued at the same pace that they were going, the question is, when will the costs of the condo in Toronto be the same as the cost of the condo in Regina? In order to answer this question, we're going to need a couple of equations. Take a minute, see if you can come up with the equations. It's too bad there wasn't some way for me to just take that text and like throw it at you guys, and all of a sudden it shows up on your page. Because
there's like no way that you could just like print out sheets. And just do that. It's like no way.
I mean,
I actually tried that once in a grade 10 class where I had basically what I have on the board here, the rough outline, and then we've just filled in as we went. But it turned out that when students weren't writing stuff down, they just tuned out completely and didn't pay any attention at all. So it wasn't very helpful.
Yeah. You have to be
Tablet desk.
Yeah, I think it's a great idea.
why don't you just make a desk?
Or just a tablet on your desk.
I feel like if this community will be more. A wooden desk with graffiti, imagine a tablet desk. Yeah. It's a scary thing.
That's why I'm thinking just desks with tablets, like a desk and you get a tablet. You have your desk right now and you get a tablet.
Does that mean you're gonna have to carry your desk and your tablet around all day?
No, just your
No,
tablet.
You might bring the tablet with you.
Instead of your desk.
Yeah.
All right, anybody get an equation yet? Jenna?
Which gives you like 144 times 1 plus 0.066.
Yeah, you got it. It's an exponential function because it's growing by 6.6% every year. So in 1 year's time, it's 6.6%. The value is 6.6% higher. And then that whole amount gets 6.6% higher after that. So this was for Toronto. And then we would do the exact same thing for Regina. Those are the two equations. We want to figure out when that's going to happen. What variable in these two equations represents the when?
In the brackets.
The x, the y, and the brackets. I have almost, yeah, it's the x, because this y value represents, right, the value of the condo at a certain time, and that certain time is going to be x. So if we're trying to figure out when these two costs are going to be the same, we need to figure out the x where the value is going to be the same. Now, we don't know what that value is. We could probably find it at some point. But for now, we really want to solve this equation. We want to set the value in Toronto equal to the value in Regina. And now we want to solve this equation for x. Which is a little bit different from what you've seen before, but it is totally doable. In order to solve this equation for x, we want to collect all of the x's on one side of the equation and all of the sort of non-x's on the other side of the equation. So I'm going to start by, and it doesn't matter whether we collect the x's on the left or the right, it really makes no difference. I'm going to just collect the x's on the right here. So I'm going to divide both sides by 72,500. So that will get rid of the 72,500 on the right. It still leaves us with the x on the left. How do we get rid of this x term, this term with the x in it, or this part of the x over here? Right, I can't take it away. Could we do something else instead of subtracting it? We can't square it. Oh, we could take the log of it. Yeah, that's not what I was thinking, but that could work. We could do that. We could do that. Can we do that in a minute? I'm going to come back to that. Because the reason why I'm going to come back to that is that there's also an x over here, right? So if we go with that strategy right now, we're going to take the log now, and we'll have to take the log of both sides. But then, actually, that could totally work. Yeah, that would totally work. All right, I'm going to do it that way. It's not the way that I did it, but that's okay. So what I was going to suggest is, hey, let's divide both sides here by 1.066 to the exponent x. Just like we divided by the 72,500. So divide this side here. Yeah, sure. Why don't we do both ways? I'll do it this way to start, and then we'll come back and do it the other way. I lost my blue pen. I don't know what I did with it. Oh, here it is. I don't think I wrote any of this down, so we'll just have to do some calculations here. Yeah. Yeah. So I do the division there. I get 1.9881. Sorry, that should be a 2. Now, if you look at this, there's an x in the numerator, an x in the denominator. It kind of makes things tricky to solve for x. We could actually write this as 1.1 over 1.06 all to the x. If we have an exponent on a fraction, that exponent applies to the numerator and the denominator. Typically, we kind of go the other way, but we can kind of work backwards here as well. Yeah, no, we're actually going to do that. We're going to do this. You just thought I should do it in that step? Is that what you're saying? Sorry. I didn't want to lose too much information there. And now you can take the log, and then there's only one x to worry about. Did I do that wrong? You're wrong. I'm just kidding. Try again. 1.1 divided by 1.06? Oh, that's why. Sorry, because I wrote the... I'm wrong. Yeah, I'm wrong. Because I lost a 6 in there. Like I made a mistake. No big deal. 1.031? 32, yeah. So now we can take the log. And don't forget, we can bring this x down in front. Can we do that right now? Is that okay if we just kind of pop it over here? I need a smaller eraser. And then obviously if we took the log on the left, or sorry, on the right, we better do it the same on the left. That's really messy. Sorry, guys. Yeah, I want you to be able to read it, though. And then from here, we could just divide both sides by the log of 1.032. Somebody will have to do that for me. I can't find the log on this calculator. Oh, I know where it is. 21.81. Anybody else get that? 82. So x is equal to approximately 22 years. Remember, x measures number of years. question asked, when will the cost of the condo be the same in Toronto as in Regina? Well, what does this number mean?
22 years.
Yeah, so this number that we started with was in 2001, 22 years later, in, what's that, 2023, I guess, right? Yeah.
Exactly.
Okay, so some of you wanted to see it sort of done the other way. I'm happy to do that. How far back do I need to go? I guess to here, right? Basically to the blue here. I think the green was where we sort of changed things up. I wonder if I could just slide all of this over and we could just do it right here, right next to it, so I don't have to try to remember all this.
That's just skill right there.
Well, all right, let's try it and see what we get. Hopefully I can squeeze it in here because it's not going to fit here. So we started with this 144,144 times 1.066 to the x. There we go. I got 2 6s that time. And we said, I think you guys were okay with the dividing by 72,500, or did you want to just do let's just do the log right from the start? Sure. Take the log of the left.
No, you have to bring the 1.10 to the bottom. No.
Oh yeah, you're right.
And you have to get rid of the 72.
Yep. Yeah, so here's why I didn't do it this way, I guess. Because this 144,144 is going to cause some problems. We could, if you really, really wanted to, it doesn't make a lot of sense, we could bring that up into the exponent, then take the log and bring the whole thing down. I think it gets a little complicated, though. Okay, good. I'm glad I didn't start down this path then, because not that it's, I mean, we would have got, yeah, we would have gotten there eventually, but I think it's a little bit more work. There is more, yeah. One more. The group that did this, I think that was Leslie and Michael's group, realized that this sort of technique either involved a lot of graphing calculator or a lot of guessing and checking. The important thing for you to be able to pull out of this is, what does it mean to solve? So not so much the how, but the what is it that you're doing. So we've kind of looked at solving the guess and check. The other one, the one that we just did, was very much an algebraic solution, which was good. And this one is going to be kind of the same idea, except now we're solving an inequality. We want to find out, when is f at x greater than g of x? Yeah, so we could do that in a couple of ways. And in fact, in this case, because of the two functions, we're pretty much going to have to do that graphically. The two ways are to graph the two functions. Pardon? Yeah, you're going to have to, well, yeah, the two ways will be graphing, but two different ways to solve by graphing. So we could graph the separate functions, graph the functions separately. Yeah, one way or the other, right? I mean, I'm going to do a rough sketch of what this looks like. And if I asked you to do this on a test, you could kind of do the same sort of thing. The log of x plus 1 is a log function shifted 1 to the left. So it looks sort of like this. And x minus 1 looks like this. So this is G, this is F. And we want to know where f of x is greater than g of x. It's basically in this section right here, from here to here. So we would have to kind of estimate, kind of like we did before, estimate their point of intersection, and then just say, hey, it's on this range right here. See how f is on top and g is on the bottom? That's how we know that it's greater than. So we would find the points of intersection. And look for where the function f is greater than the function g. So that's sort of the first method, which I think probably makes a lot of sense to you. You look at them and you see where f is on top and g is on the bottom. If it were asking the other way around, where is f at x less than g of x, then we would look for the opposite. We would look, well, f is down here, g is here, same over here, so it would be kind of out here. The second way that we can do it again is by graphing, but instead what we would do is sort of like what we did in question number 1 or example number 1. We took these two functions and we turned it into one function and we looked for the zeros. So that's the other strategy, is to collect the functions on one side. And determine where the result is either greater than or less than 0. I'll show you what that looks like sort of algebraically, at least. I won't get into the graphing. Well, maybe we will. I don't know. We'll see. But I'll show you algebraically, at least the start of it.
So if it's greater than 0, then it's greater than?
Well, it depends. So the first part here is to collect the functions on one side. So John, if we wanted to collect the functions on the left side here, we would want f of x minus g of x to be greater than 0. But if we collected the functions on the right side, we want g of x minus f of x to be less than 0. So it all depends on which side you collect and which way the sign is facing.
So if the sign was the opposite, you click on the right side?
Yeah. Well, I mean, it's not necessarily a right side, left side all the time. It depends on what sign was already in there.
But it still sort of didn't answer the question. I mean, like, if it's greater than 0, is that when it's greater than the other equation?
It depends.
Okay, so what if it's on the left side? That's this situation.
Here, let me show you. And I think that might, we can't come up with a rule that works every time. It sort of depends on, again, what side you're going to collect on, and also what's the sign that's already there. So I think after we do this, John, I think it'll answer your question. If it doesn't, just let me know and we'll kind of go over it some more. So the question asks, where is f of x greater than g of x? And f of x was the log of x plus 1. We want to know where is that greater than x minus 1. Yeah. So if we decide to collect everything on the left, we can subtract x from both sides and add 1 to both sides. Which leaves 0 on the right side. So we could graph this. I don't really have any good sense of what this looks like, but if we were to graph this, wherever that function would be bigger than 0, I have no idea. I just drew that on the board, so don't think that that's what this looks like. I want to show you what we could actually have. Why don't we look at it? Do you want to look at it? No, it doesn't.
Okay, so in this case, I understand.
You got it? I'll graph it anyway just to see, because some of you will want to see that.
Is the homework question just on the word bank?
Yeah.
1 to 6.
I was gonna actually suggest that we did. Yeah, I feel like that'd be.
Minus x plus 1? Hey, I wasn't too far off. All right, so this is what that function actually looks like. We wanted to say, where is this thing greater than 0? Well, it's greater than 0 in here. So for x greater than whatever, this looks like a 1 actually. And sorry, yeah, thanks, John. I thought this one might work out nicely too, but it doesn't. So for x greater than -1 and less than whatever this is, it's clearly something between 1 and 1.5, closer to 1.5. So maybe a 1.3 or a 1.4. Does that answer your question, John?
Yeah, it does.
So we want to see where this thing is. What did it look like again? Kind of like this. I think it went like this, right? I just had to move it over. Thank you. That's pretty. I was pretty close. I had to move it over, but. Oh, that's a really good question. So Leslie's looking here and saying, hey, we've got an x plus 1 here and a minus x plus 1. Don't forget that the x plus 1 in the brackets has to be operated on by log. Nope. No, because then you still have the same problem. You'd have the log operating on that. It's kind of like having a sign, right? We can't just take the sine of x and add that to x, because that's totally different. This thing is some number. This whole thing is some number, and whatever that number is, we have to subtract x and add 1.
So how would we know? Would we have to use graphs?
Yeah, or I could give you two functions that it was fairly easy to figure out where that's greater than 0. So if I gave you like a quadratic minus, I asked you when is a quadratic greater than a linear function? When you collect all your terms on one side, you would get a quadratic again, find the zeros by factoring, and then just look at your graph and say it's greater than here and it's less than over here. Is that okay?
Do we figure out how we were going to solve that?
By estimating either that guess and yeah. I wouldn't give you one like this on a test because you would need to have.
Maybe would we sub something in for x?
You could do that, sure.
Solve it, and then if it's less, then we play around with it until you find some value that's like there.
Yeah, so remember when we did the rationals, we kind of had to know what the zeros were? That's kind of what we want to do here is we want to find out where are the zeros of this function, and then we can test to the left and the right and see if we're above 0 or below 0. This one, we can't do it algebraically. We'd have to use a calculator. You'd have to.
What if you like did this one final integrator, but like you go log x plus 2 equals x minus 1, and then change that into exponential. And then find out what it
You still have the same problem, I think. Is that, yeah. Your final answer, though, needs to look something like this, right? We said that this point was -1 and this one. What did we say about 1.3 or something? I mean, that's what your final answer should look like because you're looking for the range of x values that produce the desired outcome where f at x is greater than g of x.
Why did we say 1.3? That's just an estimate?
Yeah, that was just based on what we saw in the graph. It was approximately somewhere in there. And what did I say? 1 to 6? Yeah, 1 to 6. Actually, you know what? I don't like question number 2 or 5. So let's do 1 to 6. How about 1, 3, 4, 6? Let's do every other one. And then we'll do 8 and 9 as well. This is 9.6. One more section to do, and we'll do it tomorrow.